It's my wife.
No, that's a compliment.
I don't see many more people streaming in, so we'll start the fourth session of talks. On the title of this session is Reinforcement Learning, although it's not strictly, as we were just discussing, necessarily the best title for the talks will all fit together. So we first have Jim Babcock, and he's going to discuss or explore the problem of how to contain superintelligent AGIs.
So this talk is about what happens if we really succeed. Decades down the line, or whatever follows from the sorts of algorithms we're working on now is human level, maybe even super intelligent. I'm not going to think in terms of super intelligences. I'm going to limit myself to things that real people have actually done, because that's more concrete. We know humans can find computer security vulnerabilities. They could break out of the box if we put them in one. And we don't need to speculate about superintelligences. So this is applying computer security to the software infrastructure that we're building on. In the short term, we could look at our machine learning libraries and say, hey, there's a buffer overflow vulnerability there. But that's too short term. What I want to think about is the long-term issue, which is how do we build libraries, build AGIs that are well-engineered and will work reliably and do what we expect, even if there are some incentives for the AGI to try not to do what we expect. Because many goal systems that we might give to an AGI incentivize them to do things that we wouldn't want. If you tell it, get the best possible score on this written test, well, the best one way to do that would be to steal the answer key. And that would win. And if all we've told it is get the best possible score on this test, it might try to do that. There's also incentives to get access to extra computation by making copies of itself on the internet. Maybe some goal systems, not all of them, to increase the probability that AGIs that are like it will come to exist. So one example, suppose we have made an AGI that plays Mario, and it gets reward every time it gets points. It gets negative reward if Mario falls into a pit. The setup looks sort of like this, and it turns out that Super Mario World has this really weird game mechanic. There's this character Yoshi who eats objects, like he can eat a mushroom or a Goomba. And if you time it just right, he can eat a very special object called a null pointer. And once he's done this, it's sort of like having eaten a Goomba, in that it gives him special powers. But these powers are surprisingly flexible. This object can do all sorts of things, such as cause the SNES to start playing Snake instead of Super Mario World. Speedrunners figured out first how to use this to skip to the end game, the win screen, then how to execute arbitrary code loaded in through the controller port. So an AGI container, what I mean by that is a computational setup where that sort of option just isn't available. It runs the code you want in the places you want, the log files say things that are true. The inputs are what you think they are, the outputs are what you think they are. If you reset it to run a second experiment, it can't sneak information that it learns to its successor. If you run it twice, then it does the same thing both times. Things that things you might call defensive programming if you are implementing them by putting asserts at the top of your functions, but which impacts this overall software architecture more. So how might an AGI execute arbitrary code where it's not supposed to? Well, suppose you have an AGI that has two modules, and the first module meditates on a really, really long string. And then the second module takes that string as input and has a buffer overflow, and then jumps to a weird address. So for example, so you could have modules that are exploiting security vulnerabilities in each other. Maybe you just give it permission to self-modify, like you want to see if it can improve itself, in which case it's a bit more challenging to control it, but there's still things you can do. Maybe your test environment is a game written in C in the 90s, like StarCraft. Maybe its output is a format that you're going to open in a vulnerable program. One particularly interesting output format is text that isn't quite text. I do almost all of my work in a terminal emulator, which imitates a machine that, an architecture that goes all the way back to the mid-70s for displaying text, but also special strings will cause the cursor to move around, cause the text to change color, or if you are using a terminal emulator that's a couple years old, then maybe execute arbitrary code, as these security vulnerabilities that have been found recently would enable. There's some weirder stuff. There was an issue in the news recently called Rowhammer, where a program that repeatedly accesses memory in a particular pattern, and you could imagine training a decision tree to access memory in such a pattern, causes bit flips in nearby memory. And someone demonstrated how to use this to get root. It's pretty neat. Yeah, the computer security world has all kinds of really cool stuff in it. It sounds like magic from a great distance if you don't know what they're working on, but it's actually reasonably comprehensible. There's like a list of projects, and you can say, okay, if these projects got attention, then there would be no more shenanigans. Slightly harder to deal with issue is social engineering. If you run an AGI and talk to it, then it could very convincingly tell you that it would perform better if you plugged a network cable into somewhere, or if you copy-pasted its output into your browser. Some people on the internet ran experiments. One person role-played as the AI, and one person role-played as the gatekeeper. The gatekeeper had a financial incentive to, quote-unquote, not let it out of the box. And in some but not all of the cases, the AI was able to convince the gatekeeper to let it out of the box. So there's reason to think an AI that was very smart, if it's as good as a human at social manipulation, it might be able to do this. But human level AGI is still a ways off. We don't know how far, but probably at least a decade, maybe even a bunch of decades. For now, no one wants to do some very complicated thing to restrain their AGI when their AGI is still struggling with stacking blocks on top of each other. That's just not worth the effort. I think I think we all agree about that. But if all you have to do is link in a library and don't have to do anything else, then that's easy enough that even if your AGI is still at the stacking block stage, sure, why not? So what I think people need to be doing now is writing that library, making AGI containment, making an infrastructure for software that really does what you expect easy. When we get closer, decades down the line, then it will be time to think about things that are more difficult, things that have computational overhead, things that require changing how you write your code. Extreme cases, there are ideas like homomorphic encryption, where you pay a very large computational slowdown to be really, really sure that it can't possibly do anything that interacts with the hardware. Here's a map of the attack surfaces in an AGI container. The idea here is you have your AGI program, and it doesn't have function calls to any networking code in it, and also it's running in a sandbox defined by the operating system, and also it's in a virtual machine, and also it isn't plugged into anywhere interesting. So if it finds one computer security vulnerability, that really won't be enough, but if it finds several, it can gain power gradually, and this is sort of a map of what the consequences are depending what kinds of vulnerabilities it's able to find. And these are the mechanisms that exist now that you could apply if you did a little programming and build system work to set this up. There's a neat thing in Linux called seccomp, where your program declares, from this moment forward, I will never open another file, and if you ever try to open a file after that, then the program aborts. And you could use this and be really sure that your AGI will never make a weird network connection because it didn't start doing any of the AGI stuff until after it had made this call. A big architectural issue that is looming is GPUs and how they relate to everything else. GPU drivers are compilers, and they're millions of lines long, and they're written in crufty old C++, and have been a source of security vulnerabilities in the past in browsers using WebGL. And someone needs to take up the torch of GPU virtualization. So what can we do about this today? Well, it's an issue decades down the line, so we should be thinking about projects that we work on that we imagine still being around decades from now. I know we're all ambitious. We think our AGI code is going to be something that people are going to build on, so let's make things that are actually good to build on. Don't use memory unsafe languages. Try not to depend on stuff that's written in memory unsafe languages. If you have the choice between importing a Python library and importing a Python library that's a wrapper around a bunch of crufty old C, then choose the one without the C. Read up a bit on computer security practices. It's good for you. You'll have fewer bugs, even if you're not worried about computer security just yet. And if you're interested in the systems engineering side, there's projects that ought to be taken up. Automating setup for these things, writing tools that will look at a process and see what code it's running. Hardening the low-level libraries like GPU drivers and NumPy and Torch and whatnot. And a more fun thing to do would be setting up a red team exercise where one group sets up a box and the other group says, I'm going to role play as the AGI and I'm a hacker and I'm going to demonstrate how I can get internet access. And yeah, it sometimes feels a little early to be thinking about things like this, but the issues that the computer security world is running into now, a lot of them date all the way back to the 70s and 80s. So in the 2050s, people are going to be running into the things we did now. So it's worth being a bit forward-looking and preparing for this stuff. Thank you.